G'day everyone, in today's ChemHill video we're going to look at the oxidation of organic alcohols as part of the Year 12 chemistry syllabus for ATAR. Okay, so the first thing we need to do is we need to go through what are the three types of alcohols. So there are three distinct types that we need to be aware of. The first one is this one. It's a long carbon chain. I've shown three here only to make it easier on the screen, but it could be one carbon or it could be 100 carbons, it doesn't really matter. But what we've got here is we've got three carbons. This is a saturated molecule, and we have their hydroxide or the OH group on the final terminal carbon. There are two hydrogens on here, but importantly, this carbon is attached to one other carbon. This is called a primary alcohol. This is different to this alcohol. Now again, carbon chain of three. That's just arbitrary for the purposes of PowerPoint and comparability between this one and this one. The hydroxide group is not on the end, it's on this carbon. This carbon is connected to two other carbons, and this is still a saturated molecule, that's quite important, but this one is called a secondary alcohol. Now you might think, well, hey, what's the difference? It's still C3HAO, C3HAO, same basic formula, but that positioning of that hydroxide makes a big difference when it comes to the reactivity of these particular alcohols. The third type of alcohol that we've got is one like this. Now this one has four carbons in it. The carbon that is attached to the hydroxide is attached to 1, 2, 3, almost making a T, and we call this a tertiary alcohol. Now this is the least reactive of the family of alcohols, but it's important that you're able to very quickly recognize which one of the alcohols you're dealing with. Again, all of them are saturated molecules. It's the positioning of the hydroxide group that's important. So primary, secondary, tertiary. Sometimes called 1 degree, 2 degree, 3 degree in shorthand. Okay, so what are the reactions of these? Now we're talking about the oxidation of these materials by an oxidizing agent or something that is easily reduced. Okay, so first of all we've got tertiary alcohols. Tertiary alcohols we'll deal with first because they're the easiest. Now what happens with a tertiary alcohol is nothing. It doesn't matter how powerful your oxidizing agent is, it will not do anything with the hydroxide group or the OH group. There are no hydrogens to remove from this carbon. We've got three very strong covalent bonds, similar to the bonds that are going to be in diamond, very difficult to break chemically. So to do anything about this, we would need some to decompose the molecule basically. So we can't do anything with this with any oxidizing agent, so no reaction. So those ones, use them straight away. Okay, secondary alcohols. Now secondary alcohols can go to a ketone. So we have one here like propan-2-ol. Now in the new nomenclature, remember that the 2 goes in here. Now with any oxidizing agent, you can turn a secondary alcohol into a ketone, propanone. No number needed for that one because that's the only position it can go to. Alright, so let's see, before we go on, what do I mean by any oxidizing agent? Okay, so there are two oxidizing agents that are typically used in this topic. Of course, any appropriate oxidizing agent with the correct reduction potential could be used, but we use these two. Acidified dichromate ions, which is Cr2O72-, they are orange and they turn into chromium ions, which are green. So we don't need a acid-base indicator for these or anything like that because the oxidizing agent itself changes colour. The other one we use is, first of all, that is a milder oxidizing agent. The second one, a stronger oxidizing agent, is acidified permanganate ions, MnO4-. Sometimes potassium permanganate, could be sodium permanganate, doesn't matter. They are purple, and they turn to manganese ions. Now they're Mn2+. Now they're pale pink on your data sheet, but in reality they're almost colourless. So to see that pale pink colour, they have to be quite concentrated. So a lot of the time we see no colour at all when manganese ions are present. Okay, let's look at this secondary alcohol being oxidized to the ketone. Now the first thing we need to do is we need to condense that formula down from propan-2-ol and propanone to something simpler. So we turn it into C3HAO. It just makes it easier to balance. This is your propan-2-ol, this is your propanone. Now we balance from scratch or from first principles, and the first step is to balance anything other than hydrogen and oxygen, and that is done. We need to balance our hydrogens next, so we add 2 hydrogen ions to that side of the equation, so we've got 8 and 8, and then we add electrons. So now we have a balanced half equation for the oxidation of propan-2-ol to propanone. But the problem with this is that this formula isn't propan-2-ol, and that is not propanone. These could be a number of different substances. So we need to expand. It's the number one thing people get wrong with these is that they get to expand it. So we expand it into the actual molecular formula or semi-structural formula like this. Okay, very important step. So there's our oxidation half equation. Now we're going to react this one with dichromate. It could be permanganate, but dichromate will do. And we get this equation straight off our standard reduction potentials chart. Now we've got two equations here. Now to combine these two half equations, we have to make the electrons the same. This half equation has 6, this half equation has 2. So we deal with that by timesing the top equation by 3. Gives us 6 electrons in both, so we can cancel them out. And we end up with an overall equation that looks something like this. Okay, so we've got 3 propan 2-ols, dichromate 14H+, 3 propanones, 6 hydrogen ions. Now there's 6 hydrogen ions and 14 hydrogen ions. So there's hydrogens on both sides. We need to cancel those out, and we end up with a balanced half equation like this. Now this would have an observation to it. This would be a clear colourless liquid added to a orange solution, and upon addition there is a green solution produced. If the organic alcohol is long, then what you might get is a bilayer forming, but this one's quite short, so you probably won't. Okay, so that's a secondary alcohol with any oxidizing agent. Okay, now primary alcohols. Primary alcohols are the ones we have to think about carefully. With a milder oxidizing agent, light limited dichromate, so if it says excess, this is not the one we're looking at, but this is limited dichromate, we can go from something like propan 1-ol to propanal, an aldehyde. Very similar to a ketone, but it's the positioning of that oxygen makes a big difference. So let's have a look at how we would balance that. We convert it down to its simplest form. Now you might say, hey, that's the same slide you had before, and it is essentially. This is why you need to expand them. Propan 1-ol looks the same as propan 2-ol when it's condensed. Propanone and propanal look the same when they're condensed, but you balance them the same way. 2 hydrogens, 2 electrons, balanced equation. Now, as I said, every single time you do this, a primary alcohol to an aldehyde, or indeed a secondary alcohol to a ketone, it's always 2 hydrogens, 2 electrons, every single time. It's never anything else. So if you remember that, then you're going to be able to double check your answers all the time, but it's never anything else. We expand it out to our primary alcohol and our aldehyde. We balance it with a suitable oxidizing agent, in this case dichromate, and we times it by 3. That means the electrons are the same in both half equations, and we combine them together and we cancel out anything excess, in this case the hydrogen ions, and there's our overall reaction for a primary alcohol to an aldehyde. Now we've got to remember, please remember this, expand this into that, expand this into that, so that we actually show the primary alcohol going to the aldehyde, not just a generic organic compound. So that's the primary alcohol with a mild oxidizing agent. Okay, the trickiest one is the primary alcohol with a stronger oxidizing agent like permanganate. Permanganate in all of its forms will turn straight through, so it bypasses, or doesn't bypass, goes straight through the aldehyde onto the propanoic acid or carboxylic acid. Excess dichromate will do this as well. It's very hard to stop it at the aldehyde, usually goes straight through. Okay, so primary alcohols can also turn into carboxylic acids. So how do we balance this one? Well, same way, condense it down into its simplest form. Here's your primary alcohol, here's your propanoic acid in this case. First of all, we've got water. We need to balance those oxygens with water. Now we add 4 hydrogens to balance out the hydrogens that is there. And finally, we add electrons. So there's a half equation. And guess what? Every single primary alcohol to a carboxylic acid. 4 hydrogens, 4 electrons on this side, and 1 water. Every single time. It's never anything else. Then we expand out our alcohol. We expand out our carboxylic acid. Still 1 water, 4 hydrogens, 4 electrons every single time. And we list that with our permanganate this time. So 5 electrons here, 4 electrons over there. We need to make those equivalent. So we'll times the top one by 5, the bottom one with 4 to give us 20 electrons in each half equation. Combine them, cancel out the electrons, and we end up with this equation here, showing our expanded formula. Of course, we've got waters there, waters over there, hydrogens there, hydrogens there. Cancel all those out, and here we've got our balanced half equation. Now this one would be a colourless liquid added to a purple liquid gives a colourless liquid, or perhaps pale pink if you want to specify the manganese ions, which is quite important. Okay, so that's the primary alcohol to a carboxylic acid. So tertiary alcohols do nothing. Secondary alcohols go to ketones. Primary alcohols with a mild oxidizing agent go to aldehydes. Primary alcohols with a stronger oxidizing agent go all the way through to a carboxylic acid. And making the half equations is really easy. Condense it, balance it from scratch, balance the carbons if necessary, but they shouldn't. Add water if necessary, add hydrogen ions, add electrons. And there you've got your balanced equation. Now, a couple of little tricks. In your observations, use the colour change of the oxidizing agent. Don't worry about acid-base indicators for this. Use the colour of the dichromate or the permanganate. Don't use universal or litmus as evidence for your reaction. Quite often you'll see students write things like, how do you differentiate between the three? Okay, so if you've got three alcohols, a tertiary, a secondary, and a primary, they'll say, add the oxidizing agent to all three. The one that doesn't react is a tertiary. Perfect, put that one aside. How do you differentiate between the other two? Well, they go, oh, we'll add universal indicator to one and one will be acidic. Well, be careful with that, because acidified dichromate and permanganate, they are going to be just as acid in the secondary alcohol as they will be in the primary, because it's excess acid. So using a universal indicator or litmus won't really work. So you've got to use the colour changes for that. You can use odours as well, so be careful with that. But just be careful just blindly using litmus to identify a primary alcohol going to a carboxylic acid. It doesn't always work. Sometimes when they go to ketones, you might notice the smell of acetone. If they go to a carboxylic acid, you might notice the smell of a vinegar type smell. So use things like that as well. Alright, hopefully that has helped you a lot in understanding the oxidation of organic alcohols. Give a huge shout out to a lot of my students who are finishing up. Faisal, this one's for you. You've been asking for a while, so hopefully that's helped. If the whole video has helped you, click subscribe, and hopefully the next one will help you just as much. Alright, see you later.